I'm a forecaster at the National Weather Service office in Caribou, Maine, and my presentation today is going to focus on forecasting run-up and overtopping. I'm going to start with, I just had one question. I have this box up on the side. Is that in everyone's way, or can I get rid of it?
You can, if you see the little red arrow, little orange arrow, you can minimize it.
Okay, why don't I do that? Okay.
Yeah, that'll help. And everybody can do the same. And let me just add real quick. We have all the audience members on mute, except for the presenter, except for Tony. The format is about a roughly half-hour presentation. If you have questions, then use the GoToMeeting or GoToWebinar features of raise your hand or use a chat box. There's a raise your hand feature and use a chat box feature, and then we'll get to the questions after the presentation. So please go ahead, Tony. I'm sorry.
Okay, I'll continue here. Going on to finding 16 of the service assessment for Hurricane Post-Tropical Cyclone Sandy in October of 2012. The National Weather Service lacks sufficient forecast guidance on inundation associated with wave run-up and coastal rivers, making it difficult to forecast impacts from coastal storms, and hence my work with wave run-up and overtopping. I'm going to introduce some tools, some parameterizations, one of which predicts run-up on sandy beaches. Another one takes that information and derives a method of determining or quantifying dune erosion. And then I'm going to talk about the overtopping of seawalls and then overtopping of stone armored revetments. First, I'll start with run-up on a sandy beach. And for this, we've been using the Stockton parameterization by Dr. Hilary Stockton. And this parameterization forecasts two items. First of all, the wave setup, which is the super elevation of the water on the beach resulting only from wave action. And it also computes the maximum run-up level, or the R2 level, which is the 2% exceedance level reached by wave incursions during a storm event. And here's the parameterization itself. And this parameterization has been ground-truthed extensively and tested in hurricanes Bonnie, Floyd, Ike, and Ivan. And real-time forecasts have been done by Dr. Stockton in every season since Hurricane Ivan. The parameterization itself requires the input from three items. The foreshore beach slope, which is measured from the high water mark up to the toe of a dune structure, the deep water wave height, and the wave length. Now, both of those are taken from the nearshore wave model and extracted from the 20-meter isobath on a line normal to the beach, and the wavelength itself is determined from the wave period. And those items are also input values that are used on the right side of the parameterization as well. The left side of the parameterization computes solely the wave setup, and the right side computes the swash running up the beach. And I should point out that the swash is a time-varying value with each large wave incursion up the beach by the swash, and the wave setup is a time average value. One other nice feature of the Stockton parameterization is that it also incorporates infragravity waves. These are long period waves of anywhere from 3 to 30 minutes. They're generated in areas of differential radiation stress in wave systems in transit from the fetch area to the coastline. I'll talk about dune erosion first using the Stockton parameterization. What we do is we take the R2 level from the Stockton parameterization, which is the maximum run-up level, and we incorporate it into the Solinger scaling model. And when we have a situation where run-up or the R2 level is somewhere between the dune toe and the dune crest. Solinger defines this as the collision regime, and this is really the point in which dune erosion begins. Now, if the run-up level comes up somewhat higher and goes over the top of the or the crest of the dune itself, this is defined by Solinger as the overtopping regime. And when this point is reached, there's much more erosion occurring to the dune system. Now, the most serious condition, as defined by Solinger, is when the setup level itself goes over the top of the dune. This is referred to as the inundation regime. And in many cases, the end result here of the inundation regime is the loss of the dune structure itself. And this is important because in many cases, as we see here, the dune structure is protecting infrastructure behind it on the landward side. And once the dune is gone, these structures are exposed to the direct impact of the waves themselves. Here at our office, we're taking both of these, Stockton parameterization and the Solinger scaling model, and we've incorporated it into a matrix. And you see here the matrix in 3 hour, I should say hourly intervals, depicts wind conditions, waves, period, the water level. And incidentally, in our workstation here, we have developed a water level grid which incorporates both the tide and the surge. And the parameter, the matrix itself also depicts the different levels in the Solinger scaling model and the conditions forecasted by it, such as erosion, overwash, and inundation. This particular sample here was taken from the April 7th to 8th, 2016 storm event, and this particular forecast was showing both erosion and overwash, but not inundation. And this is actually a picture of the test site itself. The dune structure running along a line like this is covered by vegetation, which was put there purposely because it strengthens the dune structure and guards against wave attack. So anyway, the validation for that particular event in April of 2016, the parameterization and this particular model worked very well from 70 hours, between 10 and 70 hours. It correctly forecast erosion, overwash, and inundation. The inundation didn't occur, and the parameterization and model didn't forecast it to occur, but the other two did, the overwash and erosion regimes, and they were correctly forecast by the model at our test site. Now I'm going to go on to overtopping of a vertical seawall. Here's an extreme event of what happens when large waves overtop a seawall. This is in Scituate, Massachusetts. It's the storm of January 27th of 2015, and you can see the seawall in the background here. The waves are coming over the seawall. They flooded and caused extreme ponding behind the seawall. You can see a stop sign right here with just the very top of it is showing, just to give you an idea how deep the water is trapped behind the seawall itself. Here's a side view of the event. We have the waves coming over the seawall, ponding behind it. There is a drainage system. It runs, there's several, about half a dozen catch basins in this particular basin area. It all connects to a 36-inch pipe. The pipe itself is asphalt corrugated metal pipe, and it drains under the seawall and directly into the ocean. It was designed for rainwater and not designed for large waves overtopping and flooding the area behind the wall. And here's the parameterization that I've been using for a seawall. I won't get into this too deeply unless someone wants to during the question and answer session. But Q is the overtopping volume. It's in units of cubic meters per second per meter length of the seawall. RC is the freeboard, which is measured from the top of the seawall to the still water level. The slope here is measured from the toe of the seawall seaward, and we have some reduction factors that account for some of the topographic features of the beach. And here we have the offshore wave height, which we are using for this particular model, and the period. Both of these are taken from the 20-meter isobath and derived from the near shore wave model. One thing just to step back a bit about this particular parameterization, there are other parameterizations that we can use which incorporate not the offshore wave height, but the wave height directly in front of the seawall. I haven't used these. It's a little bit more difficult because it requires determining the wave height very close to shore, directly in front of the wall. It would require a Busanesque model, which is a phase resolving model, and right at this point we don't have the computer power to run such a model, and we are talking about putting some. The SWAN model itself doesn't handle backwash or reflection from the wall or other structures, but we are talking about adding or modifying the SWAN model so it does. And here's a side view of the freeboard and the slope that we use. Again, the freeboard is measured from the top level of the seawall down to the still water level. And when I mention the still water level, I'm referring to what the combination of both the tide and the storm surge, but not the wave action. And the slope is an average from the toe of the wall seaward. I took the in this case I took the -4 level NAVD88 because it was readily available from LiDAR data. Here's a depiction of the test site. A very long seawall, over a mile long. There are two basin areas behind the seawall. I did pick this particular basin, the 7th Avenue Basin, because it was most easily we had an easy ability to isolate it from the rest of the wave action. So we picked that one. There's a staff gauge in the lowest part of the basin. It's pictured right here, and we installed a data logger at the bottom of the staff gauge, which gave us water levels in 6-minute intervals. We determined the volume of the basin using GIS. We took LiDAR data from the USGS, plotted it. Here I depicted it in 1-foot intervals and overlaid it on top of imagery so you could see the locations quite clearly. Closer look at the data logger. We deployed the data logger prior to a number of events. It records water level in 6-minute intervals, and we picked 6-minute intervals because it matches up with the data coming from the tide gauge. And since we know the volume of the basin, the volume at any time can be determined by the water level at the staff gauge data logger. And the idea of this model is to take the information coming in from the nearshore wave model, the wave height, period, water level, feed it into the parameterization. The parameterization predicts the water coming over the seawall and going into the basin. We use the Manning engineering equation to compute the flow value of the drainage system. So we know the amount of water going in, the amount of water going out, so we can determine the level of the water in the basin at every interval from the data logger. So we plotted up something like this. This event was the November 2nd event, 2014. On the left side, I've plotted the volume of the water in the basin and the level on the staff gauge on the right side. The base of the staff gauge is at 8.5, and those units are in NAVD 88. Another event, this was the big event that I depicted right at the beginning of the presentation with the flooding behind the seawall. On the left side, we can see the volume of water in the basin behind the seawall, and again the levels on the staff gauge on the right side here. You can see at this point the staff gauge at one point the deepest water level got to about 8 feet deep, corresponding with the height of the seawall itself. I'm going to go on now to overtopping of a stone armored revetment, and the parameterization for that is nearly identical to what we use for the seawall. The same input parameters here. One thing that is different, the slope is the slope of the revetment itself, and it also incorporates the same reduction factors. The input values are the same. The wave period and the wave height, both taken from the 20-meter isobath on a line normal to the structure. Here's a side view. Again, we measured our RC from the freeboard from the still water level up to the top of the revetment in this case, and we used the slope of the stone armored revetment itself. Here's the site. This is in our CWA, and again we plotted everything up with LiDAR data in 1 foot intervals. Here you can get an idea of how steep the beach is. And we also developed a matrix for forecasting. This is similar to what we use for the Stockton parameterization and the Salinger scaling model. The difference here is instead of computing erosion, we're computing, we have labeled D volume. This is the volume coming over the top of the revetment, and for purposes of fitting things into the matrix, instead of using cubic meters per second per meter length of the revetment, we use cubic feet per second per meter length, so we could fit the numbers into the matrix more conveniently. And this is the April 7th to 8th event, and as you can see here, around the time of high tide, it is computing a volume of water coming over the revetment itself. Unfortunately, at this site, we don't have the ability to compute or to validate the actual volume yet. I'm working on that. I'm going to talk a little bit about that a little bit later in the presentation. But we've developed an index, and taking those values, in this case 2, 4, and 2, we put it into the index, and this gives the forecaster a convenient idea of what the overtopping values mean. And in this case, between 2 and 4, we have small to medium-sized rocks coming over the revetment onto the road behind it. And here's a picture of what it looked like. Here's the pond area behind the revetment, and I'm going to talk about that in a minute as a possible way of validating this, similar to what we've been doing at the Scituate site. This is what I had in mind. Again, this is the aerial view of the test site itself. We have the revetment along the road here, the pond and swamp area behind it, and in the most extreme cases, the water goes over all of this and floods this area. So what I did was I used the same LiDAR technique that I used in Scituate. Determined, first of all, this is about a 20.6 acre area that floods at the highest level. I computed the volume at 11-foot elevation relative to NAVD 88. It comes to about 50,000 cubic meters of water. We then went on to examine there's one, I'll back up a bit here. Right over here, there's a culvert that goes under the road. It looks something like this on the pond side. It's a 42-inch culvert, and on the opposite side, the seaward side, it looks something like this. And what I have been doing is applying some, again, some drainage engineering equations to that to determine the capacity of the water going out through that culvert area. And here we do have a webcam. It's a live webcam. There's a motel near here. I'm just going to back up a bit so I can just give you an idea. It's located right here. There's a webcam, and the webcam is pointed out in this direction. Let me go back to that. So we're going to do two things here. We're going to probably install a staff gauge right here, and hopefully deploy a data log on it and try to capture an overtopping event. Very similar to what we did down in Scituate. Again, we know the water going into the pond area predicted by the parameterization, and the water going out through that culvert under the road. And when we get the instruments deployed, which we haven't gotten to yet, we're going to try using the same validation techniques. And so instead of the forecasters just having an index that we've developed from historical events, so we'll have some actual numbers that we can plug into this. So I've left some time there for questions. So does anyone have any questions?
Anyone who on the GoToMeeting call who has a question, please either use the chat or use the raise your hand feature inside the GoToWebinar GUI. We have a question from Bill. Bill, you are unmuted. Please go ahead with your question.
Can you hear me?
Yeah. Is this Bill Soberg?
Yes.
Yeah, please. Yeah, please go ahead.
Okay. So, do you study the frequency of these flooding events, the ponding events behind the seawall, and would you conceive that the return pipes might have to be made bigger or something? What do you do? What do you find that the communities or expect that the communities would do with this information?
We haven't talked about that a lot yet, but we've this is very experimental at this point, and the community has asked for some of the information that I've been collecting. This isn't actually my CWA. This is another office that we've been working with under the NART project. But yes, we have given them the information we have, and actually we've had some problems actually computing the water. We know how the drainage capacity, but it varies somewhat, and we initially figured that happened due to sand going into the drainage system itself. And the last event, the drainage system actually got clogged up completely, and the water rose through several. The storm went through several tide cycles. So they are aware that there's a problem there, and I don't know too much about what their plans are to mitigate it, but I think what we've done so far is help them along with that, knowing that how much. One of the ideas I did have here was I just didn't want to develop an index that the forecasters use. I wanted to come up with actual quantitative numbers, so we could give that information to engineers there, or engineers working on the development of a drainage system in other areas as well, so that we could give them quantified information which would help them in the design of the drainage system itself. Does that kind of help you a little bit there?
Yes, thanks.
Sure.
Okay, thank you, Bill, for the question. We have another question from Greg Zalestra of MDL. Greg, you're unmuted. Please go ahead.
For the Scituate case, the plots that you showed there, was that just for volume validation?
What was the last few words there? It was kind of...
the plots that you have for this Scituate, Massachusetts case?
Yes.
Was that to validate your volume estimates, or?
Yes, yes. That was the idea of that. I showed two of them, and I've actually have about 3 or 4 other events, and what I did there is we went through several events. Some of them worked really well, and others not so well. And what I did was go into and optimize the parameterization somewhat. I really didn't want to do that because what I had in mind was to develop something that could be moved to an area where the topographic features weren't there to validate it. And my future plans are when I have other sites, I have several other sites in mind that I want to do the same thing. One of them I showed the pond area in RCWA. But what I want to do is work this parameterization so it kind of works well for all sites, and it could be taken and put into a place where it wasn't possible to validate it. So that part is kind of work in progress. What I did when I optimized it, there's one of the reduction factors which accounts for shallow water. I've adjusted that somewhat, and in doing so, I got all of the analysis of each event to work quite well. The only one I wasn't able to do was the one where the drainage system plugged up, and obviously we had to wade through the water on that one to recover the data logger because the water was ponded there for several days. It just didn't drain out. Is that kind of what you were getting at there?
Yeah. I also want to know did you forecast overtopping for that particular event or not?
Yes, yes. The forecast, the forecasters in that office had some other tools, and what I did was I've been running this particular one for their area in Excel, and I spit out some calculations for a number of different storm events, and I think using this and using their techniques, their forecast did work out, and they didn't forecast specific water levels. That might be a goal, but they did forecast the overtopping. One of the issues we're working on now is with the nearshore wave model. We've been I'm not sure how familiar you are with the nearshore wave model running on WCOS, but we're sending wind grids down to the computer, and the wave model itself is run centralized. We don't. Several of the offices we're planning to do this work with are generating their own water level grids as well. For the nearshore wave model, we've been using the SDOS level. Apparently, in our office and some of the other offices, the forecasters have been doing better forecasting both the water level and adjusting the wave heights, and we're kind of working on a way that we can send not only our wind grids into the WCOS model, but the wave heights as well.
Okay, thank you.
Okay. Do we have any other questions?
Any questions on the phone or remotely? Again, please raise your hand or give us a chat. Any questions in the room? Okay, I think those are we've exhausted the questions. But I thank you very much, Tony. It was a very interesting talk. And
thank you.
This recording, this presentation has been recorded, and it will appear in the VLab Forum's webpage shortly after the talk ends, shortly after this. Thank you very much for those who attended. Next month, Steve Smith will be back, and on August 17th, we'll have Jason Burks of MDL presenting the Just-in-Time Training Plugin Project. Thank you again on behalf of the VLab Forum.